All right, now we're starting the stream. All right, so you just watched me move this thing around a bunch. So I'm gonna go through it again real quick. Um, okay, so there's good news and bad news. We got the prototype back for the second version of the pTumbler. We made a bunch of assumptions and made some changes. There's good news and bad news, and we'll go through that. So the good news is that I think that this cost reduction got us down to what the commercially available versions of this are. And more good news is I think that we can continue to reduce the cost. So the cost right now is around $330. The off-the-shelf version is $300. And there are already some changes I can make to get us down to 300 right off the bat. So I know that we're going to at least hit commercial viability in terms of cost for the open source version of this, which is good news. It means that this wasn't for naught. That in conjunction with the fact that we know it works means we've pretty much gotten to a place where we can see the finish line. So that's all the good news. Actually, one more bit of good news. This barrel wrap feature, where instead of making this out of a stack of very expensive um, plates like this, instead of doing this, we're going to wrap around some stringers 30 thou thick sheet metal, stainless, and it seems to work. That's the good news. It isn't great, it needs some love, but for the most part, it works, which is great. And it's way cheaper. So the barrel alone was about $900 in version 1. Version 2, this is down to, we've reduced the cost by an order of magnitude. This is like less than 90 now, and I think we can get it down to like $30, which, considering that this is a sheet metal barrel that we can finally adjust and tune, that's pretty great. So that's the good news. The bad news is looking at the hatch, it's pretty bad. It doesn't bend as well as I would have liked. The cantilevers here are flimsy, and I've already bent them and nearly broken them. It doesn't follow the contour because the radius is too small. It does on the cap. It does not on the stringer mechanism here. A, was a giant pain to install, but B, because that radius is so small, it's really hard to actually get the tab and slot detail sorted out and actually installed correctly. So that is going to be a problem. We're going to probably have to redesign this hatch, if not from scratch, at least from a point where we make totally new assumptions about how this latch mechanism is going to work. So that's the bad news. Some medium news is that in the meantime, between me learning that and doing this stream, I went ahead and you can see behind me prototyped a version of the barrel that uses a hatch mechanism, which is just simple screws. And so I don't love using simple screws for two reasons. Well, three reasons. One is you need these specific nuts to make this work. These are non-serrated flange nuts, and I'm not a fan of that. The second reason is because for noise and vibe, this is actually a bad idea. What is going to happen is potentially this is going to shake itself apart, and these are going to fall off, and you're going to be in a bad place when all of your media and parts fall out and this thing stalls. And then the third reason I don't like this is these nuts are easy to lose. So I can see myself putting one of these nuts aside or even putting it into the barrel accidentally, and then losing it for all eternity, and then having this entire thing useless until I find a spare or I wait for an order to come in of new flange nuts. So I'm not in love with this, but it's a good intermediary until we figure something else out. So we're prototyping right now, and in the prototyping phase, the trick to engineering design prototyping, specifically mechanical engineering, is reality is going to punch you in the face. It's looking for any reason to punch you in the face. I believe there's a law for this. I think it's called Murphy's Law. If it can go wrong, it will. So we know everything's going to go wrong. What we want to do is we want to minimize the number of things that can go wrong. And so to do that, we're going to use the method, which I'm not in love with, but we know that we can tune later once we start to reduce some unknowns around, say, the sheet metal construction of the barrel, or the sheet metal wrap version and construction of the barrel. So that's the status right now on the prototype. So I actually don't have the motors yet. They're coming in today, and so tomorrow I'll be able to actually find out if this cross section that I'm about to draw actually works using this method of torsionally coupling the shaft and then axially releasing it so that we're not over constraining the system. This flexure actually went together pretty well. Yeah, it looks pretty good. Was surprised. I made one stupid mistake. It doesn't matter, but it's an aesthetic thing. You can see the shaft. Can I get this sucker to focus? The shaft D face is actually slightly misaligned, and it's just an aesthetic thing. It isn't a performance thing, but yet it annoys me. Other things that worked, the bearings work pretty well. They're an easy install. I got the gap on that correct, and it's true for the other one as well. So the reduction in bearing cost went from 75 something dollars down to 20 total, and I think we might be able to go down further, but I think we're actually in a place where I can let these bearings live the way they are. We'll want to build a version 2 of the prototype in entirety before we make more decisions around that. Let's take some notes so that I don't forget what we need to do. Okay, so I've actually got, what we'll do is we'll go through the model, and I'll write down notes about what did or didn't work during the build and what we're going to have to change for the next version. So first things first, there were general hole clearances that needed some love. Specifically, let's see. Oh, there's actually, which hole clearances got me? Actually, I think it was misaligned holes and hole clearances. So these holes here were misaligned, I believe. I fixed them since. So that was part one that I already fixed. The second thing is this flap here. These flap a bit, and it's not great. So let me show you. You can see that they gaps because, you know, over tolerance, it's likely that you're not going to have enough material and it's going to gap. So what we're going to do is we're going to extend one of the sides to overlap. And then that will hopefully fix that. Actually, yeah, let's just write these out. Other thing was these slots need some correction. By the time I got to the third screw, it was almost impossible to get these installed. And so that's two things. That's one, increase screw clearance on, what are we going to call that? Are they flaps? I don't know. And attachment flanges. So change to slot detail. All right. So that might be just lateral sort of flaps and slots. Another one was actually detailing issue. I actually forgot a bend slot in the 2D. So I had to really wrench on one of these things to get it to work. But like I said, the good news is that general construction method seems to work. We just have to get through some of the details. And what I mean by, well, yeah, I just have to get through some of the details. Let's go through the rest of the things we talked about in Atom real quick. Rework or redesign of latching flexure. And that may not be it's probably not going to be a flexure. We're going to default probably to that stupid screw detail that I'm not a huge fan of. What else? These screws are hard to get to. So access holes for frame connection screws. Specifically, I think it was this one was a real bear to get to. So you need essentially a ratchet extension and I didn't have one. So that was pretty painful. So that's going to need some fixing. This detail here worked pretty well, these bumpers. So happy about that. But I do want to add washers because the frustrum, is it a frustrum? Frustum? Bolt frustum. Frustum. So frustum is the cone of load that a screw or bolt puts into the materials that you're or the parts that you're mating into. It looks like a cone. Frustum. Let's see if I can find a good example of this. Yeah. So the load path actually looks something like this. Nope. Looks like this. So when you apply preload to the bolt, it's actually a conical cross section that protrudes into the material. Interestingly, it's not exactly as drawn here. It's more complicated than this, but you'll see this used in really hardcore engineering around screws, like in aerospace. But anyways, that was essentially causing this to deform because this is a soft rubber in a way that I didn't like. Clamps on the bicycle seats. What do you mean by that, Jake? None of this is, by brake metal, do you mean super thin gauge? Because yeah, they do the thin gauge. If you mean by bike seats, these flanges? Yes, I did the flanges. They worked well. I used it's hard to see here, but I used a bend slot detail, and that worked well. So it's pretty good. Could have been worse, put it that way. Yeah, so I need that frustum is causing me essentially some concern here because I think this is this needs the frustum needs to increase its diameter, or we need to increase the bearing area on this bumper. It appears that you'll either tear or rip through the bumper, and then the bumper will just fall off. So we got to address that. Okay, what else? I realized that in cross section, I'm not locating this bearing axially. That might be a feature, not a bug. I think we've properly constrained this. So if you move the entire assembly to the left, you can't because you collide with the bearing cartridge here. and you're free to do it here. But if you move to the right, you collide with the bearing cartridge on the left side here, and then you can't move through here. So I think this is still okay. It's just during assembly, this feels weird because you've got the carriage bolt and the nut wrenched down as hard as possible, but it's still floating around inside, which feels wrong prior to assembly, but I think it will sort itself out once we're assembled. Oh, this is going to be changed to an M8 screw instead of this weird carriage bolt. We're going to need more room. Okay. I already did that IRL, but we just have to model it into this assembly. Oh, actually, let me take a step back. The reason, what I mean by IRL is I actually designed a CNC slash 3D printable version of this, and the cost of this thing is less than $100. It's crazy. But I'm currently waiting to finish the prototype that you see behind me before I go too deep into this. But this one's cool because you can just 3D print everything here and just order parts, which is great. And so when I say I tested it IRL, I actually went and redesigned this bearing assembly to take an M8 screw, which is off the shelf, which is great. And that's going to reduce costs because now you don't have to buy that weird carriage bolt. And the reason why you can do that is because you don't need to radially constrain the barrel to this bearing. You can just assume friction is going to do what it needs to do. This, on the other hand, you actually do need it to be radially constrained or rotationally constrained because ultimately you do need to rotate the barrel, and you do that through being torque capacitive from the motor all the way to the barrel. Whereas on this side, you don't care, so that's why we got rid of that carriage bolt and reduced some cost here. Oh, plastic barrel has some thickness issues. Before I forget, I'll add this to another list. I won't waste my time. Well, actually, I'll show it. What I mean is the thickness of this barrel here is 2, I think, millimeters. But then I accidentally offsetted it at some point. Let's see if we can find it. And so one of these is a little bit too thick. I'm not finding it. Maybe I already fixed it. Huh. All right, I'll double check that later. But maybe that's fixed already. That'd be nice if it was. Actually, there's a better way to check this. So that's 2, 2, 2. I'm looking at the gizmo to get the reading here. 2 and 2. So that's right. Let's check this one. This is 2, 2, 2, 2, 2. Okay. Maybe I already fixed it. So never mind, we don't need to do that. All right, what else we got? Let me jump out of the CNC version. And this is already available on the GitHub if you want to go prototype this yourself, but be warned that I haven't fully tested it, so your mileage may vary. For instance, this bolt hole was in the wrong place, so that's what I mean by your mileage may vary. And oh, before I forget, this was also broken. This wasn't a through hole, so as I said, your mileage may vary. So now it's fixed. I also wanted to increase the diameter on these. A little too tight made assembly kind of a pain. Same story here. This was already 4.25, but let's make that 4.5. Where else did I have this issue? can't think of it. This is good for now. Oh, I think this is a little too thick, actually. I'm wasting some material here. This is going to be, if you want to print this, you're going to print it at 100% infill. And that's a problem. Oh, this was also missing, this feature here, so we have to add that. Let's see if this is going to be painful. Hopefully I can just mirror this. I just found out you can mirror features in Shaper, and this has been a life-changing thing for me. So that means you can, not features in the feature tree here, like the history, I mean literal geometry features, which I didn't know you could do. All right, so this one isn't going to work. I'm not too surprised by that. Let's see if we can mirror this. No. All right, so I'm going to have to brute force this, and I know a way to do it. So I'm actually going to copy the entire body, and then I'm going to make a change, and then I'm going to boolean it, and that's going to take out just the stuff I want. So essentially what I'm saying is, give me just this solid here. If you flip and work, might not let me work. Can I slice it? Maybe. Okay, there we go. So what I'm going to do is I'm going to, now I've got this body, I'm going to bring it back down. And when I subtract this one from this, it's going to give me just that feature I want to save. There we go. Look at that. We're going to mirror it. And then we're going to move it into place. And then delete the redundant features over there. And now we're cooking. So this now is hopefully in the right place. We'll double check that hole to be clear. Yep, that's right. All right, so now that feature is mirrored correctly. What else are we missing? Oh, I was thinking about optimal geometry for these. So the thickness here is 5. That seems like a lot. But all of your load essentially goes through this, essentially this feature, so I'm okay with that. But it is a lot of material. So I was thinking we might lighten this just a hair by shelling it. If it lets me shell. Don't think it's going to let me. So we can brute force that, but before we do, I want to see what we're doing on this side too. So we have 5 on the other side, we have 2 here. We should probably make this 3. What happens if we go to 5? The thing is, I don't hate 5. I think 5 might be appropriate. It's just there's a lot of material I think we're unnecessarily using in areas we don't need, so I just want to lighten this up a bit. Actually, you know what? I'm getting too far into the details. That's going to be a future value DFM thing for now. We'll just make this thickness what it essentially was. Yeah, that's fine. This one should be simple to adjust real quick, so I might do that. Get rid of that shell, it broke. How do I want to do this? So I'm going to sketch on this real quick, project, and then offset by 3. And that's going to give me essentially the minimum that I want. And I'll do this one as well by 3. Yeah, that looks better. And then we'll want some ribs to carry some of this load through. We'll make that. These can be pretty skookum. They should be skookum. And actually, now that I'm looking at this, I have a washer here, and I actually think that this isn't going to be enough. So let's just go back real quick and offset this. 3 was fine.
Okay then.
Okay. Thank you, Siri, as always. Exactly when I needed you. This one we're going to do 5. Okay, and then we'll pattern this. This isn't super critical, it's just I know that we're going to be burning a lot of material and we don't need that much. So I just want to get this right. So we're going to come back, I think 2. Yeah, there we go. Turn off the sketch. And we will radius these. Now that I'm looking at this, I missed an opportunity to take advantage of some symmetry here. I should have made that a single boolean and then body, and then rotated the body, but I missed that opportunity. So I'm having to do this in a slower way, which, you know. I have to bind fillet. I unbound it. Okay. Before I forget, what am I going to bind fillet to? I think I had it bound to Alt F. Chamfer fillet cycle. Alt F. Okay. Anyways. So let's get back to the sheet metal version. Why aren't you working? Did I lose all my keylines? Shift F3, what's going on? Oh, my keyboard's busted. That's fine. Okay. Let's get back to this. So what else went wrong? So we talked about the hatch. I already fixed the misaligned holes here. We talked about clearances for this. Bearing seems to work well. The sheet metal seems to work well. Yeah. Okay. That off the top of my head is everything. So the sheet metal itself for the wrap. Yeah, I want to walk through what I was thinking about this. Okay. So because this wrap is so hard to get on, it's because the material is really stiff and it's really the thickness gives it bending resistance. And that bending resistance makes it really tough to wrap this. So I want to run through the engineering reasoning behind what the options are and why we might stick with this and just find another way to do the construction. So right off the bat, the material is too thick because that's what's giving it its bending resistance. So I'll write this out. I might even be able to show you the calcs we did before on this. No, I haven't done it. So I'll just run through the calcs real quick to show you what we're fighting against here. Okay, so we have a sheet of metal that looks like this when you look at it this way, right? And here's our sheet of metal. We're wrapping it around the stringer. So originally, when we designed this, I made the assumption incorrectly that if we are fixed on one side and cantilever on the other, we can approximate the resistance to bending by applying a load at the tip of the cantilever and approximating it as a beam and finding out what that deflection is. Um, so actually that's confusing, so let me do it this way. This is the distance of deflection, which is del. I think that's del, um, which is deflection. And so we found del, and then we found out the load that it takes to get to del, P. So we had the deflection and the load, and that was roughly telling us, is this going to be easy to handle? Where I made the mistake was, this is incorrect. And the reason is because as you wrap the barrel around, your cantilever goes down. And so this length ended up being something like this at the end. And that made it really hard at the end. So I only calculated the initial conditions and not the final, which made it really hard to do. And so the way you can do this is to, let's delete the deflection portion and actually draw this as it is, which is to say it's a beam like this. This beam is of a thickness h, which stands for height. And its width is in and out of the page, and that's b in the equations. And that equation that we're talking about right now is the second moment of area, or the resistance to bending. And that equation is bh cubed over 12. Now this is going to matter in a second when we can start comparing materials. So how do we make this easier to bend? Well, this is the resistance to bending, and this actually plugs into another equation, which is, we'll actually pull out the right equations here instead of approximating through stress. If you're interested to know what the stress is in this scenario, like when you apply this load, it's mc over I. And in a way, this kind of tells you your resistance to bending, because this is your resistance to bending, or second moment of area, and stress is equal to strain. This is stress. So roughly speaking, whenever you want to know how much deflection something's going to have from first principles, you can quickly regress that from thinking about it in terms of stress, because stress is literally strain. And trust me on that. You can't have one without the other. Anyways, so if you want to quickly figure out what your deflection in a situation is going to be, and you don't know the deflection equations, you can roughly think in terms of stress, and that's good enough for first principles in some cases. So anyways, we're talking about how do we make this easier to bend, make this sheet metal part not fight me so hard when I try to put it together. We're going to go from first principles engineering and figure out how you would do that. So stress is strain, we said that. Resistance to bending, or second moment of area, is this. And the important thing to see here is that the resistance to bending is pretty much driven or governed by the height of the beam. And again, here's our sheet metal. And and then here is this wall, which we're going to call the nearest bolt. Um, um, so we can actually go find out what this deflection is going to be if we use the beam equations or beam formulas. Um, and so what I got wrong, like I said earlier, was that this distance actually shortened over time. Let me write this out. So your L is actually the length of the beam. So this distance, this L, went down until you got into a situation where it looked like this. Because remember, as we wrap the barrel sheet metal around the cap, that effective distance gets smaller. And so that's where we went wrong. Now the good thing is, it isn't just a function of length. We could approximate it potentially by using a distributed load, which would be more accurate in a way. And so I would like to try this again by thinking of it in these terms. I think this is actually more accurate for what we're looking at. And the reason for that is because as you wrap the sheet around the barrel caps, yes, your L is going down, but you can think of this also as, well, actually, your length is going down, so we have to throw all of this out. There's a way to do this using calculus, but we're not going to do that. We're not going to make this too complicated. We're going to keep this simple. So what we're going to do is we're going to say for the deflection in the scenario I just drew, we're going to write out that equation so I can show you why thickness matters here. Actually, this is kind of cool. This gives it as a function of p. We actually do care about this in terms of a variable length. So we'll use this one. And so P essentially goes in as we attach screws. And so del is actually delta max. And so this is the equation we care about. And so let's look at this and think through how we can make this easier to bend. So delta, or del, is essentially deflection, right? And that is equal to PB PB squared over 6EI. And that's 3L minus B. Now, what can we do to make this deflection go down? Well, we can make I bigger. Wait, is that right? If we make I bigger, deflection goes down. Yep, that's right. So we actually want deflection to go up. Sorry, I said that incorrectly. We want deflection to go up. So in other words, we're saying for a fixed load, P, we want this deflection to go up, and that's roughly analogous to saying it's easier to bend this sheet wrap around the barrel because you get more deflection for the same load. B is roughly H, and actually I'm going to change that to H. And L is the length Okay, so this is a constant, so we cross this out. We could change the material potentially, uh, which is the Young's modulus here, which is the stiffness roughly of the material. So that's good. We can change I, which is the geometric properties, which includes H. So we can change these three things. We can't change L. That is what it is. And H is still this H. So really this is, I'm going to simplify this by saying this is actually H cubed here. When you multiply this out, that's true, but just for this sort of first order approximation, I think this is good enough. And we can't change H, like we said. Okay, so this is what we have to play with. So deflection, roughly speaking, and we'll make this roughly speaking here. How do I lock this? Just going to move it out of the way. So deflection, roughly speaking, is roughly the height of the beam times Young's modulus, or the stiffness of the material, times I. So this is what we can play with. I, as we said earlier, is actually equal to something else. So um, we can actually start to drop in the variables we know and see what by what factor we can actually start to make this barrel easier to wrap. And so H stays where it is. E again, we can change that, but for now we're going to leave that alone, and then we're going to substitute in the equation, which is um, BH cubed or BH squared over I. One second. For a rectangle, it is BH cubed over 12. BH cubed. Um, I think B is wrong here. What is B? Oh, right. B was the distance. B was the distance. Um, so we'll fix this as B. Sorry, that wasn't the thickness like I was saying earlier. Um, so this remains BH cubed. I think that's right. I think that's right. I'll have to come back after the stream and double check this. This assumption that this H factors in might have been wrong. I think it might actually be wrong because I think when you factor this, I don't want to spend this stream going into why this might be wrong. So what we'll do instead is we'll rewrite this real quick from the simplified case of a simple cantilever. This one. And then we'll rederive this real quick. There we go. This one. PL cubed. So this is PL cubed over 3EI. There we go. And then again, we can't change P. We can't change the constant. We can change everything else here. We want the deflection to go up. So now we think about how to do that, and we're going to do that by substituting in our second moment of area, which is BH cubed over 12. But because this is division, this actually goes up to the top. And then we kill it because it's a constant, we can't change that. So now we have essentially our equation of variables we can change. So we can change E, we can change the width. Actually, we can't change the width because the width of the barrel is fixed. We don't want to change that. So these are the variables we actually have. So now we know what to play with to make this easier to manufacture or wrap the barrel around the cap. All right. Okay. So how do we do this? Let's look at making E smaller. We could make H smaller, but I don't know that we actually can because actually I know that we can't because when I look at what's available in terms of material, we are already at the thinnest material available. We're already at 30,000. So we have to, we can't do that. Sorry. So all we have is length and we have E. Length, we can't really change because, well, length we can't really change because it's the distance between these screws, but it's real, that's an approximation. It's actually the moment, it's the portion that's cantilevered. So we can't change length either. So really all we have is E. We need to find a material with um, um, a smaller E. And so what I mean by that is we need to reduce the Young's modulus. Young's modulus is the description between deflection of a material, or I'm sorry, strain of a material, and its and the stress um, that it sees, which is roughly analogous to saying it's how springy your spring is. That's the Eli 5. So we want a smaller L. In other words, we want it to be more flimsy. And so right off the bat, steel is not listed here. Are you kidding me? Okay. Steel, I happen to know, is 30. It's actually, I think, 27, 10 to the 6 psi. So it's essentially roughly 3 times stiffer than aluminum, which means aluminum would be a third as stiff. The problem is that we have to make sure that we can get a similar thickness. And so we could get 30 thou here. When I look at the materials, the thinnest aluminum we can go to that is commercially available is 40 thou. So it's actually a little bit thicker. So now we have to see, is it worth it? 50, 52, 40 thou right here. 40 thou. That's not good. They do have it in 2024, but 2024 is incredibly expensive, so that's not going to work. So now we have the question of, does 40 thou work? And if it does, is it going to be easier to bend around our barrel? And so we can actually kind of figure that out now. So how do we do that? Well, we set our equations for deflection equal to each other. And so we'll have aluminum, and then we'll have stainless. And so that becomes PL cubed over 3E, and I was BH cubed over 12. And we do the same one for over here. But instead of drawing it out, I'll actually just, saying this is equal to this, roughly. So we can't change P, yada, yada. We already went through everything we can't change. The only things we have left are the thickness and Young's modulus. And so now we can start getting to comparing. So this is, for aluminum, 1 over E to the thickness cubed. And we'll do sub A for aluminum. That's going to be equal to the same equation, but for stainless. So we'll do that sub S, yeah. So thickness sub S. And then because they're both in denominators, we can just flip them around and they become essentially this. And so now we want to know if a thicker aluminum but a lower Young's modulus is better than the equivalent stainless. That's what we're after here. So now, to do that, we can actually do this as a comparison and say, all right, well, what is the factor by which this is true? We'll say factor del. And so here's where the fun comes. We actually do this as a ratio. So we say, okay, let's divide one into the other and get that factor. And this will be in units of unitless. But this is going to help us understand, is this new material better or worse than the old material? And so we will divide, this by this. And just a reminder, the reason we're doing this is because we can get the material, aluminum, which has a lower modulus of elasticity, but it's thicker. And so we want to see, okay, well, that's great. Does that actually result in better performance for us? Given that, yes, steel is thicker, but it has steel has a higher Young's modulus, or it's stiffer, but it's thinner. We're going to see if this actually outweighs the benefit of the Young's modulus of the aluminum. So we're going to write this out in our equations, and we're going to go find out real quick. All right, ignore the streaming question that I asked. Okay. Oh, right. Um, I'm just gonna, I happen to know the Young's modulus off the top of my head, so we don't need to look that up. Let's see if this works. Hopefully it does. And it does. Go ChatGPT. Okay, so let's write that out. How do you do delta? Is it del? Yeah. All right, so let's write this out in Python. So E sub s is going to be equal to, that's steal, so that's 2.7, 10 to the 6. E sub a is going to be 10, or it's 1. Actually, this is 27. This is 10. And then H sub s is going to be 40 thou. And H sub aluminum is going to be, I think we said 40 thou actually, and this is 30. And I think that's it. Yeah. All right, so now we can get our answer. So del factor is equal to E sub s times H sub s cubed divided by the same thing but for aluminum. And then we get our factor. So it is roughly 14% better to use, yeah, that's right, 14% quote unquote better to switch to the aluminum. So 14%, that's it. Despite having 3 times less modulus of elasticity, because the thickness is related by a factor cubed, it kind of makes it pointless to switch because that the factor of essentially this in the term just totally wipes it out. So in other words, it's saying it's not really worth switching and that we can actually kind of stay with what we have so far. So with that knowledge, actually just as a sanity check, I want to make sure that it's not even worse by, well, no, I know that this is smaller, so yes, this is better. This is better. Okay. Okay, so there's our answer. All right, so that's done. Now we know that we're going to stay with the stainless, and we are going to look at this from a mechanical design perspective to understand what the best path forward is. So this is done. All right. Before we get cooking on CAD, I want to make sure there was nothing else that I was forgetting to address. So actually, the way I take notes on prototypes, especially if I know that they're not permanent, but I actually like to take Sharpie and actually write directly on the part. It's pretty fun. feels good to write on the part. Yeah. Okay. Let's get to figuring out what did or didn't work here before we keep going in CAD. We haven't tested the motor yet. This needs a little bit more room potentially for the control box, but I'll wait to see till the build's finalized. Oh, these PEM nuts were awesome, by the way. They worked easily. It simplified the installation super by a ton. As a matter of fact, I think I might actually switch the rest of the assembly down here. Actually, that might fix this part of the assembly if I switch these to PEM nuts. It's just that they're a little bit more expensive, which is a bummer. But it honestly simplified the assembly so much that I'm entertaining actually doing it anyways. Actually, you know what? Before I get to CAD on this, I'm going to finish the prototype tonight before I get started on the CAD because something I learn here might affect the rest. And instead, I'm going to take care of something I've been meaning to do, which is on version 1 of the prototype, I'm going to rework this hatch. So we'll do that. And by the way, the version 1 of this prototype is my goal is to leave this as a revised version and continue to maintain it because I think that this is actually still desirable, specifically um, because I think that it being waterproof might be a feature. So the other ones aren't going to be waterproof. They have to go into a warehouse environment and they have to essentially be protected from water. But this one I liked because, well, it wasn't waterproof, but it was water resistant, and that might be something that I want to have an option for. So we might carry 3 versions of this. This version, which is water gestures. What the hell are you talking about? No, I don't want gestures. Um, so we have A, B, and C. A is water resistant and rugged. It's hard to break. Like, trust me, I can throw this thing around and it's going to break whatever it runs into, which is kind of cool. B here is the super cheap version, and C, I named this incorrectly. C is the 3D printed slash, if you want, CNC'd or cast version, which is going to be super cheap. It's the cheapest version you can make at the cost of reliability and robustness. So most robust, most expensive. Um, Anyone can buy and make this. You don't need a 3D printer. Well, asterisk, you might need a 3D printer. I still have to adjust the design potentially. And then this one is, if you have a 3D printer and want it as cheap as possible, this is actually the cheapest way to do it. So those are the 3 versions for now. But anyways, I want to get back to this hatch. I think this hatch needs a little love. And the reason is because I actually 3D printed this hatch temporarily out of PET. And despite what I've been told about it being highly temperature resistant, it still failed because plastic um, is a garbage material. And I have to, how do you ban users? I have to ban my first user. This is great. For spamming. I don't know how to ban users, so just deal with that later. Um, yeah. Anyways, so plastic's not a great material. It creeped, or I believe it's cold flowed or cold worked. I think it's cold flow. Cold flow. It cold flowed. and worked itself into not working. So, um, so I want to rework that. I already got started on this by switching it to the design I talked about earlier, which is using a stringer. My concern is that the stringer isn't going to work super well. In general, the radius is just too tight. Um, yeah, the radius is just too tight. So we either have to increase the radius or we have to make it not round, which I don't want to do. Let's isolate the barrel. And this is no longer a sheet barrel. Where's that hatch? It's a little in there. Okay. So I added this stringer to add some rigidity, but I don't know that I need that stringer anymore. That cross brace. I don't know that it's doing anything. Yeah, if anything, I need it at the ends. Oh, I remember. I actually wanted to prototype something here. So this is what I was thinking. Because this is such a bear to bend, I was thinking we could do something like this. So here's the outline of the stringer, and that defines the shape, right? Of the sheet. What I was thinking was, what if we came up and picked up the top and sort of encapsulated it? And I'll draw a big gap to kind of representationally show what I'm getting at. But the idea is that you actually slide this sheet in like this. And it lives in this slot. That's what I'm thinking. And I think this might work. So I want to try that out. Some challenges are this, there's a minimum feature size from here to here. And that's driven by CNC laser DFM requirements, essentially. There's a minimum feature size that we want to find. Countersinking, tapping, yada yada. Before I forget, let me add to the to-do list. Okay. Let's see if we can get the DFM stuff on this. Resources, all guidelines, CNC, laser, which is what we're going to do. So minimum is what we're looking for. Minimum requirements. 50% of the material thickness. And so this is a thick material. This is right now 1/2 inch, which means it would have to be at least 6 millimeters, which is too much. So we actually want these stringer sizes to go down. So the stringer size would be something like the thickness would go down. And so actually we can quickly figure that out. So this is 30 thou thickness, which is 0.76 in metric. So 0.762 divided by what was it? 50%. So we need at least so we ideally want the thickest, a 1.6 thick stringer, which might be doable. That might actually be doable. They do make 1.6. Would it work? So this is 3.18, and it's Skookum. So 3.18 would work. This is 1.6, and I think it would work. Actually, I do happen to know it will work. We can use 1.6. The good news is that's going to make it cheaper too. So, yeah, it's nice. It does change the design a bit. Here especially. Forget about this. We want to tap this for that. Yeah, we want to tap this. How do we get around this? I guess we could use two nuts. All right. So we want this to be 1.6. Let's just get this roughed in, and then I'll figure out the stupid issue here. What I'm getting at is the issue is that we actually have this spring plunger, and that hole's tapped for that. And so if we made this 1.6, I don't know that that's going to be strong enough to handle the bending, but B, yeah. And actually, I remember why I added the stringer now. It's because I want to handle bending from this corner all the way to this corner. It's cantilevered essentially from this lock, so we actually do want the stringer. But that can go down to 1.6 millimeter as well. So what was this part? This was, let's go look at what this was. I think we can fix this by just using two nuts. I think this was M12. Or was it 1/2 inch? What's going on here? What are we doing? What are you? 3/8, 16? That's not right. That's not right. Yeah, it's not right. That's the wrong part number. I clicked the wrong thing. This is what people call a skill issue. When did I click? Not found. Same as. They removed it. They removed my beautiful spring plunger. No, there it is. M12. Okay. So we need some M12 nuts. That's not impossible, but what I'm getting at is we'll have a nut on both sides to lock it in place, and I think that will work. We still run into the issue of this not being strong enough, but We'll see. So we need M12 nuts. And I bet you they're stupid expensive for some stupid reason. Thread size M12. These are getting pretty big, so yeah, yeah. This was M12 by 175. M12 75. Where's my nuts? Hex M12 175. And I'm getting I don't love spending $9 on nuts. Can we just consider an M12 nut half-inch screw? I guess realistically we can not include that in the BOM. Yeah. All right. No threads because we're not psychopaths. And we'll change this to 1.6 and we'll get back to work on this. Yeah. This is way bigger than I was expecting. We're going to need 2 of these to locate it properly, so a little worried about that. Actually, we can bottom it out on this and we only need 1 nut, so it might be fine. Let's see. So we have this in the position we want it. So we isolate all of this. Yeah. Put this in place. And we want this to be 1.6, so we'll pick it up on this side. This hardware has to change. Distance is center 6, so it's going to be 6 plus half of the sheet metal thickness. Yeah, looks right. Gotta put those nuts in place too to make sure that this is right. Correct. And then this, we want to get rid of these features. Actually, and we need to slice this away because we're going to delete this all and copy it over because we're good at modeling. Okay. This one is also going to go down to 1.6. Actually, we'll do the math on this one. So 6.35 minus 1.6, 4.75, and we're going to do this to both sides. So 2.375 is the offset distance. Did that incorrectly. No, I did this correctly. What's going on? Yeah, okay. Going crazy. And then we'll move these the appropriate amount. Why? Ah, yes, of course. That's why. Why wouldn't you? Okay. And then this can come back in a bit. We don't need all that. Actually, just slice that. Extend this out of here. Keep it 0.5 millimeter. And then we only need a chamfer for that. Why? Why? Why didn't... Not mad. All right. So... that radius... I don't like that radius. So we're going to fix this. Because we're not engaging with the material very much. We actually want to change this cut relief. Okay. Now we have more contact area here for that stringer, or for that brace. This minimum material is spooking me a little bit. It's our edge distance. Before it was fine because it was thicker, but we have less overall shear pullout area. 3.5. Yeah, we can't really go any further than that, so we might have to just live with that. Hmm. Actually, we can help a little bit. If we pull this out of here, give ourselves a little bit more area to distribute that load with. We'll look for the max value here. Max parallel. 4.295. Actually, is there a better way to... Is this 6.25? Just brute force this. It should work. What's the radius over here? 2. Make that 2. Okay. All right. So let's get that screw over here. So it looks like we have decent room. the question becomes, is it strong enough? And I think the answer is yes. I think it is. Because this brace is going to help with the bending there. I think we're going to be okay. I'd hate to be wrong, but I think we're going to be okay. We have to fix this cutout too, but I think we're getting there. So let's fix that cutout. Ooh, I bet there's a quick way to do this. We have to fix this too, so first the cutout, then we'll fix these holes. So I'm going to just slice this, brute force it, and then kind of push and pull to get it right. There we go. We have a clearance here of, what is this clearance? 1 millimeter, so we want 1 millimeter here as well. And I'll do that by just moving it to this face and then offsetting it 1 millimeter. Great. And then here, actually before I do that, I'm realizing that I'm bugging this radius out, so to make it clean, I'm going to come back here and make this 1 actually, and then do that to these radii as well. So that should unbug. Here we go. That radius. Perfect. Okay. Now we fix these holes. This one will be easier. I think we can just boolean the hardware. So literally, so actually we'll delete these features. And then we will subtract the hardware. And then we will adjust those radii. And I think this is ready to boolean now. So we'll mirror this over. And I'll pull the section out a bit so we can get a look at what we're doing. Okay, and then we'll boolean this out after we mirror it. Okay, looks good. Oh, we also need to boolean the stringer. But I should do that while I still have that mirror plane. There we go. Oh, I forgot this distance. What was that? .8. And I need to mirror that hardware, and then I think we're pretty much done with this. Again, I need to step back in history to pick up that metal plane. Does that work? Oh, I forgot. These gaps are wrong too. Um, yeah, I need to fix these gaps. I forgot. So I actually had to file these down. It was really embarrassing. Um, might have already done that though. One second. Okay, I think that's fixed. Appears to be so. Um, fix these screws and nuts. Do this side too. Okay, I think that's good to go. The question becomes, do I want to make this symmetrical to save money? But it looks stupid. And the answer is yes, because if the stringer doesn't work, I might want to copy this detail over to this side, so that way you have two spring plungers to lock this into place. Actually, no, the stringer should work. We'll do this if we have to. We'll come back and do this. I'm not going to be lazy. I'll just spend the extra money right now, but yeah, we're going to do this correctly. And then, there we go. Oh, this actually needs to be a little bit longer because if these bend out of the way, then this tab will fall out. In other words, if it bends um, like that, you'll actually dislocate with your tab. So we should be super conservative on this dimension. Yeah, yeah, we should do that correctly. Okay, glad we caught that. Let's come back and fix that. So the way we'll do this is we'll just move this, give ourselves something really conservative, 5 millimeters, and then we'll offset these, something like that. Yeah, perfect. I don't like these. Yeah, we have to do the same detail with, yeah, we have to fix these as well. The dog bone, that is. Can we actually just delete face on these and then redraw them? Yeah, we can. Good. Okay, so we'll redraw these. Get my symmetry planes. Make these tangent. Make this 1. And then we actually just, how do we do that? We make this tangent Yeah, make this tangent, and then we make it coincident to this point. There we go. So now I can mirror these. And then subtract them. So these dog bones are going to enable the stringers to have a little bit more material engagement. Or just engagement. It's made out of materials, redundant to say material engagement. There we go. That's much better. We have clearance all around. It's looking good. Okay. Now I think we're done. A little worried about this cantilever. A little worried about it. But we will build and see. Actually, we have to add that location detail here, but I have to run, so we'll do that tomorrow. All right. Thanks for joining. I will see you next time.